Hi, we chose to work with electrocardiogram or ECG signals of a human heart for this project. ECG is used for detecting abnormal heart rhythms. Our group consists of Arif, Mohammed, Tony, and me, Fatima. The signals have been collected from the database PhysioBank ATM. The signals that we chose were 3 recordings from a 25-year-old male that have been recorded on different occasions. The recording method was a single lead ECG method with 2 electrodes placed on each arm of the person. Using this method, small changes in the electrode will not affect the signal. Each recording lasted for 20 seconds and had a sampling frequency of 500 Hz. The ideal ECG signal consists of a P wave between 0.67 to 5 Hz, a QRS wave between 10 to 50 Hz, and lastly a T wave between 1 to 7 Hz. There are some typical noises in the ECG signals that we had to remove in order to get close to the ideal signal. We started off by loading the signals and plotting them in time and frequency domain. When looking at the time and frequency domain, we can see some high and low frequency noises as well as the power line noise at 50 Hz. Power line noises is caused by electromagnetic interference such as electromagnetic fields by nearby machines or improper grounding of the machine or the person. Offsets, shifting of the signal up and down, and were also present in the time domain signal. This is caused by the low frequency noise, baseline wonder. Baseline wonder is caused due to skin electrode impedance, respiration, and body movements. Another low frequency noise is electrode motion artifact, caused by alters in impedance in the skin due to skin stretching. And lastly, EMG noise is a high frequency noise caused by electrical activity of the muscles.
Before gathering this data, some key characteristics got to be known about the signal so they don't get accidentally filtered out. There are a lot of different filters, and FIR and IIR are the main two classifications that can be used, and these filters are mostly used in different circumstances. IIR are mostly used for offline data, meaning we have all the data downloaded on our computer, and from all of these different IIR filters we chose to work with the Chebyshev Type 2. Type 2 filters have ripples in the stop band instead of the pass band, which makes it a smoother response in the pass band. A high pass filter had to be made to filter out the lower frequency noises. According to the study we did, theoretically an ECG signal should not have any frequency lower than 0.67 Hz. Therefore, we made a fourth order high pass Chebyshev Type 2 method, also called inverse Chebyshev. Chebyshev Type 2 has a lot of wanted features like a steeper roll-off than Butterworth filter. After filtering, we can see the magnitude of the frequency below 0.6 has been suppressed, and we can show it right now. Let's start off with this one. This one right here is the non-filtered one, and we can see it in frequency domain that we still have a lot of frequencies. We have magnitude right here between 0 and 0.65 or 67 actually. Same thing with this signal right here. And it's all of this that we were trying to filter out, heavily suppress. All of this, turn it to 0 or closest possibly. And if you look at this figure right here, figure 5, you can see that we tried and accomplished it. So you can see here below 0.67 hertz that we don't really have that high of a magnitude on the frequencies, and we do right here on the unfiltered one. We have a baseline wonder in the first figure and not the fourth one, because the base wonder was caused by the lower frequencies that got removed away.
When it comes to low pass filter, there are many types of high frequency noises in ECG signals, as 50 Hz noises and noises over 50 Hz like EMG. And we see also that the signals still very noisy. Therefore, as a first step, we use a very common method, which is moving average filter with 7 points window size to smooth our signal. We tested out many window sizes, and in the end, we used the 7 points window that gives us the best result. Like we see, after using moving average filter, in the time domain, the signal starting to look like a readable signal, but filtering process is not finished yet. And we see also that the power line noise is still visible in the frequency domain, in addition to some high frequency over 50 Hz. To process these noises, we need an IIR notch filter. So we designed a band stop filter using the Butterworth method to remove the unwanted noises. We choose Butterworth from order 4 because it has a flat pass band and a flat stop band, which means there are no ripples in both bands, which will not affect our signal in a bad way. Because of that, this filter was the best choice when it comes to removing a specific unwanted noises. Disadvantage in this method is that transition between pass band and stop band is not too fast, but it is not a big problem in our case. However, we choose to filter the signal 2 times using notch filter. The first step was to removing power line noises between 49 and 52 Hz. And second step was to removing the high frequency over 49 Hz. And like we see here, this figure is the original unfiltered signal in time and frequency domain. And this one is the original filtered signal in time and frequency domain that we get from the FISOPank ATM database. This one is our work, what we have done, and like we see, it's very similar to the original filtered signal.
Here is the final result between the unfiltered original signal and the final filtered signal in time domain. As you can see, we removed the baseline wonder with the high-pass filter Chevy, and we also used moving average to smoothing the signal. Here's the signal in frequency domain. We remove the 50 Hz power line noise and the noise is over 50 Hz with a notch filter. We can conclude from our result that the project was successful. In the end we got a good result which is greatly similar to the original filter that we downloaded with the unfiltered signal with the database Physibank 89. There's the same final initial signal that we filtered. Here's the filtered signal that we downloaded with in time domain. And here's all the signal in frequency domain. In the end, we can extract data from the signal. In other words, we can extract the P, QRS, and T segments. In this project, we used a high-pass filter Chevy to remove the baseline wonder, a notch filter to remove the 50 Hz powerline noise and the noise over 50 Hz, and also moving average filter to smoothing the signal. We also tried to filter out between 7 Hz and 10 Hz, but it was not successful and it corrupted the data in the signal. Thanks for watching.